Get ready for a fast-paced Ohm's Law and Power review. First of all, let's take a look at what we call a simple circuit again. A simple circuit has a source, in this case a battery, and a resistor. And just a single loop here. And this is just showing an AC source and an ammeter rather than this notation for the circuit. Ohm's Law, the fundamental concept in circuits, and in this case with voltage. As we've seen before, if our potential difference increases for a given amount of resistance in a circuit, in other words the voltage is getting bigger and bigger, the resistance is staying the same, then we're going to get more and more current because we have more work per charge, and yet the resistance is the same. If we keep the potential difference or the voltage the same and we increase the resistance, then the current is going to decrease. Put those two ideas together and you get Ohm's Law. Therefore, the current is directly proportional to the voltage or potential difference and inversely proportional to the resistance. If you take Ohm's Law, this is the basic form of it, because current is dependent on both the potential difference and the resistance. But using a little bit of algebra, we can also represent it as V equals I times R, and R equals V over I. A lot of people, when you ask them Ohm's Law, they'll use this form, although this is really the more proper form of Ohm's Law. So using Ohm's Law here, we in a simple circuit, you can calculate the current if that's our unknown, if we know the potential difference and the resistance, just by using our Ohm's Law equation and plugging in. And so 12 volts divided by 4 ohms is 3 amps. Of course, we could have done this in any form. If we want to know the resistance, we could have taken 12 volts and divided by 3 amps and got 4 ohms. Or if we wanted to know the voltage and we knew the current was 3 amps, we could add I times R. 3 times 4 is 12 volts. Power is up next. Power in general is how much work you do in a certain amount of time. So the more work in less time means that you are more powerful. In electrical systems, we remember that voltage or potential difference is equal to the work per charge. So voltage is work per charge, and current is charge per time. So we can see here that if we multiplied voltage times current, the Q's would cancel here, and we would get back our general form of power, work divided by time. Therefore, power in electrical systems is voltage times current. So P equals V times I. Now, that's measured in watts. Power is measured in watts, and it's kind of interesting because Watt really didn't do much with electrical systems, but he did do an awful lot with power systems. 1 watt is equal to 1 volt ampere. Power in circuits. Usually when we're talking in circuits, we talk about delivering power. In this case, a battery delivers the power, and then the power is used in devices like resistors and transistors and so forth. So power is dissipated. Sometimes we talk about power is dissipated or used in the resistor, and it's delivered by the power source. Power equations are standard one. P is equal to V times I. Using some algebra, we can also rearrange things. So I is equal to P over V, or V is equal to P over I. We also have these two equations which are used quite often with power. If we use Ohm's Law, V is equal to I times R, and plug IR in for V here, we can also see that power is equal to I squared times R. So this power equation is quite useful when you want to know about power losses in conductors, when you know the current flowing through the conductor. So P is also equal to I squared times R. And then if we don't know the current but we know the voltage, we can use Ohm's Law here. I is equal to V over R, and plug that in for I here. and we would get another equation, P is equal to V squared over R. So this one's useful if you don't know the current, but you know what the voltage is. So if we're going to calculate power in a particular circuit here, and we know voltage and current, then we could find out the power pretty easily. Voltage times current is equal to 360 watts. And we could also, if we knew the power and voltage, we could find the current. And if we knew the power and the current, we could find the voltage. Also, our other power equations that we talked about previously, I squared R. So if we knew the power was, or let's find out what R is here. R is equal to V over I. So 120 divided by 3 is 40 ohms. So if this is 40 ohm resistor. So we could also find a power if we knew that was 40 ohm resistor. I squared is 3 times 3 is 9, times 40 is the 360 watts. We also know the voltage here. If we could use our other power equation, V squared over R. So V is 120 volts. 120 squared would be 14400, 14,400 volts squared. That divided by 40 ohms would give us the 360 watts as well. So you could also use V squared over R. So those are all the power equations here. Again, power being delivered and power being dissipated in the resistor here. A nice simulation from PhET. If you type in PhET, Ohm's law, you can play around with the resistance and voltage and so forth and get an intuitive sense of Ohm's law. So, again, that was fast and furious, and here's Scratch's parting idea. All right, well, hopefully you are doing more than meditating on your quest for continuous improvement.